Welcome friends to this new lecture of week 6 of Soil Science and Technology, and in this lecture we will be completing the soil acidity which we started in the last lecture, and then we will be discussing about the soil alkalinity as well as uh, and also about the soil sodicity and other problematic soils. So, in the last lecture we covered up to this, and we started about we are going to start about the amelioration of the soil acidity. Now, amelioration of the soil acidity is generally done by application of liming materials. The generally the most common the most common material which the farmers and apply for correcting the soil acidity is called the lime or calcium carbonate. Some other examples of liming materials are dolomitic limestone, that is calcium magnesium carbonate, and then calcium oxide, magnesium oxide, calcium silicate, etc. As you can see here. Now, I have given here the reaction of dolomitic limestone. So, you can see the dolomitic limestone is reacting with the water as well as the carbon dioxide, and this carbon dioxide basically occurs into the soil due to microbial respiration, and as a result of that the bicarbonate and bicarbonate ions are formed. Now, this bicarbonate is very reactive in removing the residual and exchange acidity. So, you can see this bicarbonate ion can remove these exchangeable H plus and L3 plus, and and ultimately these exchange sites are occupied by the calcium ions, and this is how the application of liming material ameliorate the problem of soil acidity. So, let us move ahead and see what is the relation between the ground limestone to raise the pH to a certain pH, that is 6.5, and initial soil pH. So, you can see the amount of lime used depends on the pH target, the depth of the application, then buffer capacity of soil, liming material used, and the fineness of the liming material. Obviously, the fine texture soil fine texture soil need more liming, and as their buffering capacity, as their buffer capacity to resist the change is more, and the split application of lime is thus recommended. So, in case of fine texture soil, obviously their buffering capacity is more because of high catenation capacity, and so you can see here in this graph. Obviously, there are 5 different types of soils, starting from clay loam to sands. As you can see that clay loam is exhibiting the highest CEC. So, obviously, the ground limestone required to raise the pH to 6.5 is is quite higher in case of clay loams as compared to sands. So, let us move ahead and see what are the other ways of ameliorating the soil acidity. Obviously, using organic matter is another way, because they bind with the aluminum and reduce their mobility, and aluminum they are very toxic in in acid soil, and the complex aluminum, this organic matter, basically the humus humus portion, basically they form complex with aluminum into their non toxic form. So, these are the beneficial use of organic matter in case of acid soil. Now, another one is the growing of differently adapted plants. For example, it is a very practical solution, and crop native to acid soil can be cultivated in a acid prone area, and also through genetic engineering and new resilient varieties is being developed all the time by plant breeders. So, we can use those tolerant crops for this type of region. So, guys, we have completed this soil acidity, and the reference is again the Nature and Properties of Soil by Niall C. Brady. So, I hope that you have got some you have got some knowledge about the soil acidity. obviously let us move ahead and see what is soil alkalinity and salinity. So, these are two important problematic soils which we are going to discuss now. Now, the concepts which we will cover are the causes of alkalinity and salinity, then how we measure salinity and alkalinity, then classification of the saline soil, and then how to reclaim and management of reclamation and management of those saline and alkaline soil. Now, let us see what is the causes of salinity. Obviously, saline soils are generally developed in arid and semi-arid condition, and in this condition you know that evaporation or evaporative demand is more higher, and evaporation should is more is higher than that of precipitation. So, as a result of that, the pH of the soils are generally sometime greater than 8.5 or less than 8.5. So, saline soils are developed in crop field not only due to the climate, but also due to the use of saline irrigation water and poor drainage condition and weathering of salt containing material. So, these are couple of reasons of this soil salinity problem. So, let us move ahead and see what is the reason behind and what are the causes of high soil pH or soil alkalinity. Now, there are different different ways of creating soil alkalinity. First of all, there are different sources of soil alkalinity, and also there are influences of carbon dioxide and carbonates for development of soil alkalinity. Finally, there are roles of cations like sodium versus calcium, and then influences of soluble salt levels. So, we will discuss them one by one. So, let us start with the source of alkalinity. Now, you know that calcium, magnesium, sodium, potassium do not produce protons after reacting with the water as aluminum does. So, these are the basic cations, and these basic cations do not produce also hydroxyl. So, these basic cations do not produce proton or hydroxyl. However, these hydroxyl ions are produced from the dissolution of calcium carbonate, that is calcite minerals and bicarbonate. So, as as you can see here, the calcium carbonate or calcite being dissolved into calcium 2 plus and carbonate, and this carbonate is basically dissolved in water. So, further this carbonate reacts with the water to produce bicarbonate, and as you can see the hydroxyl ion is continuously generating. Then in the next step, these bicarbonate is again will react with water to produce carbonic acid, and then again the hydroxyl ions, and this carbonic acid again will dissociate to form H2O and carbon dioxide. So, you can see these calcium carbonate, basically due to the presence of carbonate, they are basically generating these hydroxyl ions, and as a result of this generation of these hydroxyl ions, ultimately the soil pH is getting increased. So, this is one of the reason of getting the alkaline soil. So, remember this equation will be required for understanding our next slide. So, if we see here, what is the influences of carbon dioxide and carbonates? So, if you go back, you can see at the end the carbon dioxide is generating. So, the starting obviously calcium carbonate and carbon dioxide. So, the generation of soil alkalinity obviously depends on either the precipitation of the calcium carbonate or the removal of carbon dioxide. So, in which direction the reaction will move will depends on these two factors. First of all, the precipitation of the calcium carbonate, and as well as the evaporation or the removal of carbon dioxide which is produced. So, if we see, the amount of carbon dioxide in soil is always more than atmosphere because of respiration, we know that, but it will reduce the pH of the soil, driving the reaction to the left. So, if you see the previous reaction again, if the concentration of the carbon dioxide is higher, obviously the reaction will drive in the left direction, so or the reverse direction. So, obviously there will be reduction of the pH, and as a result of so these carbon dioxide do not help in generation of the soil alkalinity. Now, the increase in pH obviously will stop pH top, and when calcium increases the soil solution as it increases the precipitation of the calcium carbonate. Now, you see in the previous slide, calcium carbonate dissolution is required for the generation of alkalinity. However, if the calcium concentration in the soil solution increase, so obviously this calcium carbonate will precipitate, and when it will precipitate, obviously the dissolution will be reduced. So, when the dissolution of the calcium carbonate is reduced, obviously there will be less generation of alkalinity, or the soil alkalinity generation will be stopped there. So, the calcium carbonate precipitate at pH 7 to 8. So, in calcareous soil the pH never goes beyond 8.4. So, this is very important. The calcareous soil is the soil where you will have high amount of calcium. So, calcium carbonate precipitate at pH 7 to 8, and in calcareous soil thus the pH never goes beyond 8.4, because calcium carbonate is not further dissolving out. And if, however, if sodium carbonate is present, which is more soluble than calcium carbonate, obviously the pH can be increased up to 10.5, and this type of pH you can see in case of sodic soil or alkali soil. We will see that. So, further another cause is the role of cation, that is sodium versus calcium. So, sodium carbonate is more water soluble, as I have already told you, sodium carbonate is more water soluble than that of calcium carbonate. So, it produces more hydroxyl and carbonate, and it increases the pH up to 10. So, obviously you can see here sodium carbonate is dissolving to produce the sodium cation as well as carbonate, and which will ultimately increase the soil pH, this carbonate. Now, another cause is influence of soluble salt level. So, the presence of salt like calcium sulphate, sodium chloride, sodium sulphate, calcium chloride, these are neutral salts. So, etc. will reduce the alkalinity, because the presence of common ions, like in case of the presence of common ions, for example in case of sodium chloride. So, the common ion here is sodium. So, the presence of sodium, or in case of calcium sulphate, the presence of calcium will drive the reaction to the left side. So, this is called common ion effect, and this common ion effect will reduce the dissolution of calcium carbonate and sodium carbonate, because already the common ion is present in the soil solution. So, as a result of this, when these type of salts are present into the soil solution, obviously the reaction will go to the left side, and obviously the soil alkalinity will reduce, or soil alkalinity development will be stopped. Now, development of salt affected soils, obviously accumulation of salt in non-irrigated soils and irrigation induced salinity, alkalinity are the major reason for salt affected soil. You can see here a white crust of soil found in case of in a highly saline zone of soil. So, these are two important reasons behind development of salt affected soils. So, in case of accumulation of salts in non-irrigated area, you can see here under the deep rooted perennial vegetation, as you can see here. So, this is a deep rooted perennial vegetation, transpiration obviously is high and the water table is kept low. So, this is one condition. So, if we go for agricultural operation there, so in case of agricultural crops, the length of the roots are small obviously, because they are the field crops. So, the shorter length of the field crops, shorter length of the root of the field crops causes groundwater to rise by capillary flow to the surface, and as a result of this, these groundwater laden with salt will go to the top of the surface and then deposit there, and as a result there will be salt sieve formation or salty soil formation. So, these are two reasons of saline soil development in non-irrigated soil. However, in case of irrigated condition, the irrigated water may contain huge amount of huge or very less amount of salts, and if the field has not adequate drainage system, continuous evaporation accelerates the chance of salt accumulation, because the salt laden water will move towards the surface of the soil by capillary movement, and then there will be deposition of the salts. So, salt tend to accumulate at the highest point of the soil surface, from which part evaporation loss is the highest. So, this is very important point you should keep in mind. Now, how we measure the soil salinity? Obviously, there are different methods for measuring the soil salinity. If we want to measure the soil salinity of a sample, soil sample itself, Obviously, there are 4 to 5 different ways. First of all, ECE, which is basically the conductivity of the saturated extract from water saturated soil paste. So, we will make a soil paste and we keep it overnight and we extract the water and measure the conductivity. So, this is called ECE. The second is ECP, which is the conductivity of the water saturated soil paste itself. So, if we measure the conductivity of the soil paste itself, we call it ECP. Third one is ECW, that is conductivity of the solution extracted from soil water mixture, usually either 1:2 or 1:5. It is one of the major most common adapted practice in laboratory measurement of soil salinity. So, generally we measure the 1:2 1:2 soil water suspension. We make a 1:2 soil water suspension and then we dip the electrode to get the electrical conductivity. ECS is basically the conductivity of 1:1, 1:2 and 1:5 soil water mixture itself. So, when there is a mixture itself, we dip it the electrode of the EC meter and then it will give us the ECS reading. Finally, TDS is total dissolved solids. So, total dissolved solids in water or the solution extracted from the water saturated soil paste. So, it measures this salinity. And another other two methods for measuring salinity in bulk soil in place is ECA, which is apparent conductivity of bulk soil sensed by metal electrodes in the soil, and secondly ECA, which is electromagnetic induction of an electric current using surface transmitter and receiving coil. So, there is a instrument called EM instrument. So, this EM instrument basically measure this electromagnetic induction and indirectly it measures the soil content of the soil. So, nowadays some advanced sensors are measured, advanced sensors are produced in the on the go, basically they are on the go sensors. They are fitted into the driving vehicle and this driving vehicle basically surrounds that field, they go through different parts of the field, and as a result of that you can see there is a real time generation of soil salinity map. So, these are some advanced method of producing the salinity map which are generally being adapted in advanced countries like US and Europe. So, these are some common methods of measuring the soil salinity. So, let us go ahead and see what is the measurement of sodium status. So, now we have covered the salinity saline soil. Now, let us move toward the sodium soil. Now, excess sodium destroys the physical properties of the soil, which is called the sodicity, and it can be measured by the different equation based on the relative amounts and the flocculating ability of the various cation present. So, one of the major indicator of sodium status is ESP or exchangeable sodium percentage. Now, the formula of ESP is basically exchangeable sodium over the cation exchange capacity by multiplied by 100. So, ESP measures the degree to which the exchange complex is saturated with sodium. Remember that the cutoff value of ESP is 15. If the ESP value of a soil is greater than 15, then the soil is considered as a sodic soil, and pH values of those soil is generally greater than 8.5. Now, another important index of sodium status is sodium absorption ratio or SAR. Now, it is the second most easily measured soil property that it is becoming more widely used than ESP, and the SAR gives information on the comparative concentration of sodium, calcium and magnesium in soil solution. Now, you can see the formula of SAR, it is basically the sodium concentration over the over the square root of half of calcium concentration and half of magnesium concentration. So, when sodium, calcium and magnesium are the concentration in millimole, millimole of charge per liter of the sodium, calcium and magnesium ions into the soil solution. So, in SAR value, again remember that in case of SAR the cutoff value is 13. So, when the SAR value goes beyond 13, that means it is a sodic soil. Now, SAR value of 13 is equals to ESP value of 15. So, these are basically equivalent. Now, it is basically used for characterizing the irrigation water. So, we have learned there are two index of soil sodium status, or sodium status of irrigation water. One is the ESP, that is exchangeable sodium percentage, the cutoff value is 15. If it is more than 15, then the soil is sodic. If it is less than 15, soil is non-sodic. And there is another sodium absorption ratio, or SAR, which is where the cutoff value is 15. If it is more than 15, then it is if it is more than 15, then it is sodic soil. If it is less than 15, that is non-sodic condition. Now, classes of salt affected soil. Obviously, the classes of salt affected soil, you can see there are three different types of soil. Obviously, one is saline soil, or white alkali soil, and saline sodic soil, and finally the sodic soil, which is black alkali soil. Now, regarding the structure, the saline soil has very good structure, whereas the saline sodic soil has good structure. However, sodic soil, the structure is destroyed. We will discuss why. The second, pH in case of saline soil is around 8.5, and in case of saline sodic soil it is from 8.5 to 10, and in case of sodic soil it is generally greater than 10. Now, in case of EC, obviously in case of remember one thing I forgot to mention, that in case of saline and non-saline soil, the cutoff value is 4 decisiemens per meter. Now, this is decisiemens per meter is the unit of measuring the electrical conductivity, and 4 is the critical value. So, the 4, when the soil is having more than 4 decisiemens per meter electrical conductivity, then the soil is saline, and when it is less than 4, then the soil is normal. So, you can see here, in case of saline soil, obviously the EC is greater than 4 decisiemens per meter. In case of saline sodic soil, it is also greater than 4 decisiemens per meter. However, in case of sodic soil, it is less than 4 decisiemens per meter. In case of saline soil, obviously it is not sodic, so it is less, ESP is less than 15. So, and in case of saline sodic soil, since the term sodic is there, obviously the ESP will be greater than 15, and obviously in case of sodic soil there will be higher ESP, or greater than 15 ESP. The SAR in case of saline soil is obviously less than 13, and in case of saline sodic soil it is greater than 13, because the sodic term is there, and in case of sodic soil obviously it will be greater than 13. What are the major ions? Now, major ions in case of saline soils are calcium, magnesium, sulphate and chloride, and in case of saline sodic soil, obviously salts of calcium and magnesium with some amount of sodium. However, in case of sodic soil, they are mainly sodium and carbonate and bicarbonate. So, the predominance of sodium in the soil exchange complex mainly makes the soil sodic in nature. So, we have seen the classification of the salt affected soil. So, let us go ahead and see some more important aspects of sodic soil. The sodic soil are perhaps the most troublesome soils of salt affected soils, and basically the EC is less than 4 decisiemens per meter, but the SCR, that is the sodium absorption ratio, is greater than 13 and ESP is greater than 15, and the pH of the sodic soil exceed 8.5, rising to 10 or higher in some cases, and the high pH is caused due to the presence of sodium carbonate, which is highly soluble. So, the soil contains high amount of carbonate and bicarbonate ions in the solution, obviously, because so either there is a sodium carbonate or sodium bicarbonate ions in the solution. They are produced in high amount, they are present in the high amount, and at this high pH, at this high pH, when the pH goes beyond 8.5, sometimes 10, the fulvic acid and humic acid, I will discuss this later on in details. This fulvic acid and humic acid, these are two fraction of humic, these are two important fraction of soil humus. We will discuss in details when we will discuss the soil organic matter. Now, for the time being, you remember that this fulvic acid and humic acid, fulvic acid and humic acid. These two at high pH they will dissolve, and when the water evaporates, it can give the soil surface a black color, because humus is by nature black in color, and these soils thus are called the black alkali soils. So, sodic soils are also known as black alkali soil when they are black in color due to the due to the dissolution of fulvic acid and humic acid due to high pH condition. Now, why these sodic soils creates physical degradation? Now, you see here obviously when the exchange complex is dominated by sodium, they create this slaking, swelling and dispersion, and obviously there are two causes of soil dispersion. One is high sodium and low salt concentration obviously. So, you know that in case of soil colloid, we have already learned that without it there is no hydrated ions. So, if there are no intervening hydrated ion, then short range van der Waals force would cause collide to the and form the coagulation or form the the aggregates. So, the van der Waals force will dominate in case of absence of any hydrated ion, and when these tightly bound hydrated ions like calcium are present in the colloids. So, colloids are still close enough to cohere by van der Waals forces, you can see here. So, the presence of calcium can produce the soil coagulation. However, when the loosely bound hydrated ions like sodium is present, colloids are too far apart to cohere by the van der Waals force, and as a result of that there is a complete dispersion. So, when there is a complete dispersion, obviously there will be soil crusting and all these unfavorable condition will be there, and as a result of this there will be germination problem for the soil, because all the germination problem for the plant, because all the individual soil particles will clog the soil pores and they will restrict the water and air movement from atmosphere to the from atmosphere to the soil, and ultimately this will also reduce the germination of the plant. So, this ultimately creates a very unfavorable condition for crop growth. So, the plant growth is hampered due to the toxicity of sodium hydroxyl and bicarbonate. Obviously, this is another reason. So, toxicity, the plant growth is hampered due to the toxicity of sodium hydroxyl and bicarbonate, and these soils have basically columnar structure. We have learned about the columnar structure. So, these alkali soils will show you the columnar structure as you can see in this picture, and they are having extremely poor soil physical condition, slow permeability to water, and air and clay dispersion reduces the crop productivity. And so, these are some features of soil alkalinity or alkali soil. So, what is the leaching requirement? This is another important term. So, the leaching requirement is basically the amount of water needed to remove the excess salt from the saline soil core, and let us see what is the salt balance of equation. So, salt balance equation shows that SIW, which is salt from irrigation water, plus SP, which is the atmospheric deposition, then SF, which is salt coming from fertilizers, then SM, that is soil coming from minerals, equals to, the summation is equals to obviously which is soil which is present in drainage water, and then SC, which is crop removal, salt removed through crop removal, and SDW, which is salt removed through drainage water, and obviously salt precipitated. So, chemical precipitation of the sulfates and carbonates. So, these are also important. So, these four processes generally balances themselves. So, this is called salt balance equation. So, guys, let us stop here and we will start from here in the next lecture, and then we will see the equation of leaching requirement, and we will solve solve some problems of leaching requirement. Till then, thank you.